Thanks for the kind introduction. And so, yeah, I'm from EPFL, and we would like to give some very broad introduction on what is collaborative learning. So don't worry if you have not heard about this topic before. I'll try to give a broad overview. So in the first part, I would like to explain a bit like what's the idea of collaborative learning. And learning here is mostly the training of machine learning models. There's two important variants which you might have heard of. One of them is federated learning. And then maybe in the second part, if you have a bit of time, to talk a bit more about LLMs and how that could then maybe finally fit together with these two parts. But I have to be honest, the last part is really a bit of open work, how to combine these two aspects. But before we get started, before we get to the building blocks of the collaborative aspect, just a very short run through on like the building blocks of machine learning itself, so and more precisely on deep learning. So is to learn algorithms which learn from data, and we use data from the past, training data where we have input-output. We use that to train our black box. This can be the weather of each day. And how that really works is just the magic building block is in the middle. It's the neuron, the artificial neuron, which just takes all these inputs, which are numerical value, combines them in a way. So how could we do that? For example, we could take a weight for each input. These weights are numbers. We could have a high weight for an important weight and a lower weight for a less important weight to predict the output. So combination would mean maybe just to form a linear combination. So that is what linear regression is. I'm sure you have seen this, and that's what a neuron is. And when we go to neural networks, it just means that we don't do this only once, but we do this many times. Maybe here is a bunch of neurons who all have the same job from this input data to predict the output, as we saw before, but now there's several of them. It gets even more practical, more expressive when we add depth to it. So here we have more than one layer. And again, what a neuron anywhere does is from its intermediate input, it will predict the value on the output such that it's most useful for the final task. And the whole training algorithm is important. That's why I mentioned this. Is like we need to find out for each weight here, and there's a lot of weights, we need to find out how we change them. Should we increase or decrease this weight? And the easy way to do that is by just checking what if should I increase or decrease. So I need to know the change rate of the output with respect to that weight. And the change rate, so how much would my output change if I make it so smaller or larger? So that's what the gradient is with respect to this one number, this weight in this case. So that's deep learning, and I'm sure you've all seen this, but now that we have learning, so now that we have the basic algorithm, we will then talk about the privacy aspect and how many maybe different collaborators can do this jointly. So learn this entire set of weights, not alone, but jointly. I'll go to the main part now. So we want to do collaborative learning. What does this mean? So the idea here is that we don't only have one worker, but we have a whole bunch of participants in the system, and together they try to do learning. So what does that mean? Like each of these 5 participants has a bit of data. And the goal of the overall federation, so the goal of everyone together is the following. It's to train on the joint data, to train on the data which is globally a little like this. But the problem is that everyone only has a part of that data. So this one only has the red part, and this participant here only has the blue part. So we want to do training together, and we want to find the same model as if the data would be centralized. But it's not centralized, right? The data is distributed. So that's why we now have a slightly more interesting version of the problem. And what we do is we will just send our updates, and the updates are changes to the weights, right? As we saw before, right? So this worker wants to increase the weight, this one wants to decrease, and so on for different weights. So they just send their updates, and we add them up on the server to then formulate a joint update reflecting the global data. by just adding them up, so averaging them. And what that means mathematically is to minimize the same function as if you would minimize the loss on the joint global training data. So these participants, they could be different things, right? They can be people, or they can be organizations of different granularities. They could, for example, be hospitals, which each has data about a different population of patients. Also, these hospitals might be located in different countries, in which case, from a legal perspective, it's very interesting because you're not allowed to actually take the data out and put it into one place, right? So you're not allowed to just take these 5 data sets, put them here and train. That's not how it works. You must use something like federated learning because the data must remain where it is, and that's the whole idea of this federated training that I'm describing. But these agents could also be different things. They could also be mobile phones, and every time you use your mobile phone to write something, a system like this with federated learning is actually used, and it's used to predict the next word when you type, right? It's going to help you type, and this way making it easier for you to write stuff. But of course, what you write, the data that you've written in the past, is very sensitive, so you don't want that to go to a central database, so that's why we would like to have a federated learning version of this. And again, the algorithm is super simple. Everyone computes their own gradient, sends this update to the weight to the server, but the good thing is we have not sent data, right? We only have sent a gradient, then we have to be a bit more careful to make sure that does not leak any additional information about the actual data. Okay, so to have a bit broader perspective again, so the old school way of doing it is this, and interestingly, that's exactly where we are now with large language models. So large language models are all centralized at the moment, so the data goes to one place, then the model is trained, and then, yeah, that's it. But what we would like to have instead is federated learning, or like what I more generally call collaborative learning, is that the data stays where it is, right? But instead of sending data, we send model updates. So this, when you have a helper server for that, coordinating this adding of the 5 updates, that's called federated learning. When you don't have a helper server, then we call this decentralized learning, where here the nice thing is that the users can decide on their own on who they want to work with, right? There's no server which decides that this is the problem that you might want, you have to collaborate on, but here they can find their own collaborators. It's also interesting to ask if, of course, these users might not all have the same learning task, right? So then you have a heterogeneity of tasks, and that's something that we're going to talk about a bit more in the next few minutes. And also where this network is coming from, right? Could this be a physical network of like undersea cables or so, where you need to respect it, or mobile phone constraints where not everyone has phone connection to everyone? Or could this graph also come from the heterogeneity, that you want to collaborate with people who are similar enough to you so that you actually learn something useful from them? Okay, so the first aspect, the first kind of building block I'd like to discuss of this type of learning is the communication aspect. And it's funny that the algorithm we discussed before, the algorithm is always the same, right? It's just gradient descent, right? And it's just adding the updates together. So it's funny, right? We have actually just renamed the algorithm to be federated learning, but I mean, you have known this algorithm on a different name, right? It's just parallel stochastic gradient descent, right? It's the same thing. Everyone using a data center to train, or using more than one GPU to train, uses the same algorithm, right? Every one of your 5 GPUs does a few updates, and then they get averaged. So you form a batch of these 5 parts, and that's it. Maybe you do several updates before you average, but that's, I think, a minor aspect. So it's just parallel stochastic gradient descent. Now, I showed you what is a gradient in deep learning, right? It's funny because if you look on the left here, what I find fascinating is that it's very cheap. It's very cheap to compute and very fast, right? So there's a neural network. I don't know, it goes from left to right or the other way. You go from the input to the output, so you compute these predictions. That is linear time in the number of weights, right? You have these input vectors. Vectors are always tiny. But then, of course, the weights themselves is a big matrix, so you have to multiply the weight matrix with a vector. Then you get the output, and then, so fine, that was linear time. I mean, in the size of the weights. And then you do backpropagation, the same thing again. It's, again, linear time, and now you use the transpose of the weight matrix. Anyway, why am I talking about this? Because now we have a gradient, and we want to send it to our collaborators or to the server. But communication is expensive, right? So communication can be several orders of magnitude slower than if you have something directly in the main memory or whatever the when it remains on your compute device. So you cannot easily send the same thing that you compute. So if this backpropagation is so fast, then even sending this vector to another node might be 1,000 times slower. So and also when you now start to say, I want to compress this method, I want to compress these updates before I send them, then your compression also has to be pretty fast, right? Because if the compression operation is slower than the gradient computation, so that's what we did here, then there is no point, right? If that compression operation is so slow, then there's no point in compressing because you want to gain overall time, right? So we need a compression which is also linear time. And here is really the easiest one you could imagine, and that's just taking the object we want to compress. So that's the weight matrix. Actually, it's the matrix of weight updates, which is a gradient, but it has the same shape as the weights. And that thing is whatever. If you have 100,000 neurons in a layer, then this is 100,000 square, so it's a big object. And you multiply it with a random vector. So that's a cheap operation. What you get from this is a random projection of the object you want, so kind of a sketch. And the idea is that you do this with the same vector on the right-hand side, so you use the same random seed as your collaborators. So because we all use the same random seed, we all compute a sketch on the same base vector here, so that what the result is going to be a linear sketch of the sum of our things, right? Because now I have a linear operation, and in the end, I'm not interested in these 5 individual updates, but I'm interested in the sum of these 5 updates. So here you can just see one of the updates. So the nice thing is this power iteration, if you just do it once, it remains a linear operation. And so that's why I'll mention this again in a minute, why this is helpful in the distributed setting. And yeah, power iterations are fast, which you already said. And in terms of size, of course, this is very advantageous because this was 100,000 square, and now what we need to send here is just the result of this computation, which is just a vector, not a matrix. So we save a factor of 100,000 if that would be the size of this matrix squared. Okay, and again, some more properties that this has is that you can use it to figure out who should talk to whom, right? You don't need everyone to talk to everyone. But what we just said is that this operation is linear, right? So in general, compression operations are not linear. If you have 2 compressions of 2 separate things, it's not the compression of the sum, right, in general. But for us, it is, because we use the power iteration. Now, if you have that, it's nice, because then the communication is much easier. Then not everyone needs to talk to everyone, but you can do what's called all reduce. Whenever you get partial results, you just add the sketch. You add the compressed versions, and then you add the final compressed version of these 2 final things, and you're done. The result you have is a correct compressed version of the sum of all the input things. So that's why you can directly plug this into all reduce. It works out of the box. And it also is nice in view of heterogeneous data. We'll mention a bit more, because heterogeneous data means that everyone needs to be represented, and you need to be careful that you still have these unbiased estimators of everyone when you form the summary of everyone, which here is the sum of these 4 compressions. So this is integrated into PyTorch. If you use distributed training in PyTorch, it uses this algorithm. And there is actually also a nice thing. This is very easy to extend to the decentralized case. When you just have 2 nodes which want to compute such a sketch, it's very easy to, again, agree on a random seed and then have them compute the average of their two models between two nodes. So for those of you who know, these are like gossip-based algorithm which averages the model with each other. So you can also use this trick in that setting, and then you get a compressed version of decentralized stochastic gradient descent. And it's also used in industry for text, multilingual text, and also for image models. Although the DALI is already outdated now, but you can use this if you have big models, because then the gradients are big. Okay, I want to discuss a few more building blocks, and especially aspects of heterogeneity, which I think is super crucial. And there's one thing I was just saying is like the data heterogeneity, right? So everyone might have a bit of different data set, and we should just not assume that all things are IID. And there is one idea which I'll just explain in a second, which is quite easy to understand, trying to get everyone being fairly represented. Then we also have a question if models are not the same, like some devices might have lower capacity, might only be able to fit a smaller model compared to other devices, like on a phone, you cannot have such a big model as on a GPU. And there is also two ideas I can mention about this. And finally, the task. So this is a bit related to the data, but you could take this even further, right? Tasks is more general. It can be that people have completely different learning tasks. They don't know what the other people's goal is, and you need to actually figure out who do you want to collaborate with and who could be helpful for you. So there's no notion of label or so on, so you need to be more general. And also to deal with errors. Right? In a federated learning setting, maybe if the data is corrupted on some of the clients, you need to have ways to deal with that. And also some software we are developing. Okay, the first aspect on heterogeneous. So this is quite intuitive. I'm showing here just two clients, which means two tasks, right? A user is kind of the same thing as a task. So if the user learns alone, then they would just go to the blue minimizer, the minimizer of the blue task. If the user, the second user, it's the green user, if they would train alone, they would go here, which is the perfect, I don't know, zero training error for the green task. But that's not the task we want. Well, what we want in federated learning is the sum of both tasks, so which is the same thing as training on the union of the two data sets. So, and that minimizer would be maybe in the middle here. So we need an algorithm which can deal with this heterogeneity, which does not drift too far away from this. So if you do standard federated averaging, what you do is a few local learning steps, and then you average between the two. And then again, you would drift again, maybe do 3-4 steps alone, and then average again, average the model parameters. So this phenomenon is called client drift, and it can slow down the training. How can we avoid it? So the problem is that the blue trajectory is very biased, right? Because while the blue worker is training alone, they only see their stuff. So every update they do is completely biased in the sense that it's not representative of the joint data set. To fix that, we need to use updates which are representative of the joint data set. It's a very naive thing you can do is to use global momentum. And that's the red arrow here. So because we know that, I mean, after we have averaged, then yes, then we are representative of both data sets. So the step you have after the communication is good, right? It's not very frequent, right? We have to wait a long time until we get such a red unbiased update. But there's a simple thing you can do. Instead of just getting it every 4 steps, we could just, we don't have it available so often, but we have it from the old round. And what we can do is we can just locally apply it in every step. So even if you don't have the perfect fresh red update, we can just apply it while we do this local training, and then we have less drift, right? If you do the blue worker does this small update from the unbiased red vector, he adds that in every time, then you have less drift. And that's what the algorithm does. And you can analyze this, and you get that this converges even in the heterogeneous data case. But we need an assumption on the amount of how different can these two tasks be. So you want that the gradients of the two tasks are not getting too far away from each other, so this is some kind of task similarity. Actually, there's even a stronger assumption that we need. So we need that the two tasks need to be that much related that their quadratics they have the same shape in the landscape. That means that the Hessian of the two tasks have to be similar. So on the positive side, this is a good bridge to the Hessian AI initiative, and on the negative side, this is a strong assumption, right, that the Hessian similarity of the two functions needs to be very close. A good thing, though, also is that this algorithm doesn't need any additional memory, so you can run this with a kind of infinite pool of devices, which is important when you go to the cross-device setting where there might be millions of participating devices. So you cannot, on the server, keep any information about each device. So this works well, and is similar to the methods used by Google at the moment on phones, where they have this challenge of heterogeneity, of course. And that would finish the first part about heterogeneous data, and I have a completely different story, which is still a bit related. It's more related also to the tasks and to people having different goals, and that's when, now if you hear this, all nice, right? But you might think that, is this really robust? Can this be broken? And of course, this can be broken very easily by just one malicious agent. And by malicious, I mean they could just send an arbitrary update, kind of trying to break the update of the good workers. So these three here might be good. We want to compute the sum of these three good ones, but unfortunately, the bad one here just sends maybe the opposite update of all the three others, and then they cancel out with all the good progress. The model of adversary reviews here is a Byzantine adversary, so that they can really send arbitrary updates. So the question is, given we don't know who is the bad worker, right? They can really do arbitrary things. They're all-knowing. They can collude with anyone they want. There's also some of them are just malicious for different reasons. They might just not be available. The question is that can this aggregation here, which is usually just a naive sum, can this be made robust? So the easy thing you do is you just use the median instead of the mean. So that works in a sense. Have to be a bit careful what it means, the median of a vector, right? Because one thing you could do is just use coordinate-wise median. Now the good thing is that this cannot be biased by one worker anymore. Actually, you can fix this to up to 50% of the workers or so can be malicious, and we can analyze this and give guarantees that the training convergence guarantee we can give is that you are actually as fast as if just the good workers would train, basically. There is a bit of a slowdown with the number or the fraction of Byzantine workers that we might have in a maximum, right? You just have to be conservative. Let's say I will think that I might have at most 20% of Byzantine workers in my system, and then I can use this scheme to make my training algorithm robust. And that's the idea. You have to be careful that this is not only done once, right? But this is done a million times over time. So over time, actually, even if you have only a small error here, over time this error might accumulate, and the bad guys might exactly make you accumulate in the wrong way. So it's quite challenging to analyze this, but this can be done as well in the federated setting, and we have a follow-up work where we try to do this for the decentralized setting as well, when then it becomes even more funny, because depending on the graph topology, you might be surrounded by bad workers or not. Hopefully you have a connection to a few good workers as well, and good graph connectivity. So that is the Byzantine learning part. And then I'll go a bit more quickly on the other ones. I just want to mention interoperability as well, and this bridges nicely to the multimodality as well that we had mentioned in the previous talk and even before. So what if, like in a medical setting, for example, sometimes you have different modalities. You have clinical data, you have image data, and you might have text data of this patient. But then of another patient, you only have text. So what do? How do you make these still work together? So there's missingness, right? And the fact that this patient does not have an image you have to be very careful about that, right? The fact that this image is missing, that correlates with the outcome, for example, with the disease. So we have to be very careful to deal correctly with this missingness. And this is an empirical project we were running to have one encoder for each modality and train them to deal with arbitrary missingness practically to still get good accuracy. But I don't know how to analyze this theoretically, but I think it's promising to have such multimodal encoders and also have them in the federated setting. And then this one is easy. So just to go a little bit further, one thing I really do not like too much about federated learning is that we have this global objective where we say the goal is the goal to satisfy the sum of everyone, but who is everyone? Who is part of this sum? So what I think is more clean is just to say that everyone has a different objective. So every agent wants to learn their own learning task, which is Fi if you're agent I, which is here. Or from the perspective of this particular agent, you would then ask, who could help me, right? So the people who might be useful for this agent, they might be different people than the ones who are useful for that agent. And by useful, I just mean that accepting this help, you should be faster than training alone. That's the notion of usefulness we have here. And what I think is very interesting now is to find the collaborators, right, without making any assumptions. So I want to get rid of this strong assumption. I mentioned that the hashings are similar or the tasks are so similar. I don't want that. I want to, in a real world, right, you have no idea what is the data quality of some agent that you encounter, but you need to decide, do I want to exchange knowledge with that agent, right? So you need to learn something from them, gain their trust, and if you like it, you will establish a link with them and hopefully be faster than training alone. So this kind of knowledge exchange, and we have one preprint where we try to work on this. This is based on building trust, based on the predictions of people. You can also use maybe you look at their gradients and look at if their gradient is close to your gradient, you build trust. Here it's using a holdout data set and say that if they make similar prediction on that holdout data set, then you start to trust them, means then you give them more weight when they give you updates in the learning. So I think that's interesting because if you do prediction-based instead of gradient-based, then you're also able to learn with different architectures, which of course you cannot. If you use gradients, then everyone must have the same model, which is a big restriction as well. All right, so we have a few use cases where we deployed this. This was nice because it was in an international context with an NGO where we used photos which were taken of a disk here from glass, which is filled by a bacteria germ, and the white dots here are antibiotics. And the task is just to figure out which of these white dots has the widest radius in killing the germ. So, and then that's the antibiotic that the doctor will like and will then give to the patient. And that's the idea. But this is in different countries and different antibiotics and new ones come up and so on. So you need to update your ML model, but you're not allowed to take this data out of the country. So it's really a perfect use case for federated learning. And it was also nice because in this case, they already had a working mobile app where it was not federated, but then we could help them by adding the federated aspect to it. And this is also mobile-based. So this is based on this software library that we develop in JavaScript, actually, but all the other stuff we do is more likely in PyTorch. All right, so this already mentioned. I'm almost done. So for LLMs, there's a bit of history, a history of scale and so on. And I'm not going to say what an LLM is, but really encouraging you to try it out. There's this really nice code base, only 300 lines of code to get started with LLMs from Karpati. So I really recommend it. And you can run small models on one computer in a few hours, right, which produce English text. I mean, it's not perfect, it's not very intelligent, but it's really good English. And when you scale this up using exactly the same algorithms as we discussed, right, you use standard data parallelism and a few more tricks, then you get really good models. And the nice thing here is that the task is so simple to predict in the next word, and got us to find such impressive generality, right? That from some dummy training task, you become very versatile. I just want to mention more the second case, which is really the challenge that remains to do, right? To really bridge this together with federated, to achieve more privacy, right? I mean, we had already, I mean, in your phone, it's already using a language model, right, to predict the next word. But these are small language models, right? They were, I think, traditionally based on LSTMs and so on, the one you have on the phone. So what's now not clear is like how this can talk to the large language model. I think that's a really cool open research challenge, right? To make big public models work together with small private models in a privacy respecting way, right? So that I think is really cool, and I think one way to go is maybe, as I said, we cannot use gradients because these are small and a big model, but maybe we can do something prediction-based, or we can do maybe something like split learning, where part of the model is done on the big model, and then the last layer or so is done on your phone. So these are interesting challenges on how this can be trained collaboratively, or even just at inference time, like when you use these models, can you use it at inference time in a private way? That's also interesting. I also find it fascinating that the same models work on proteins or genetic data, can sometimes even predict the shape of proteins just from the, I mean, not perfectly, but it's such a simple training objective that it's surprising that it's, to achieve this simple objective, it does quite smart combinations to do so. So this, I think, is fascinating, and one thing that we worked on is to make the context longer. So this has nothing to do with collaborative learning for a moment, but to just group, we want to have more visible context, and we do it blockwise by having a special token which is representative of the block of tokens. If you want to have attention to something inside the block, your attention must first go to the special token and then go to the respective token in the block, and you can see that this will approximate the true attention over all tokens, and it's kind of, it's nice that it's kind of the true attention. It's not just a recurrent thing where you slowly forget the past, but it's attending to the true thing, and you get a kind of a reduction in computation by a factor of this block size, which is like 50 in these practical applications. So that's just to say that I'm quite fascinated about LLMs, and we work to bring the two things together, but that is really open work. I talked today about the efficiency, right, when you talked about communication compression. Scalability is kind of the same thing. Privacy, I didn't mention much, but we do use secure multi-party computation to only reveal the sum of the updates, but never an individual update. We talked about robustness, right, when there is a fraction, 50% of workers can be malicious. And then incentive of fairness, which is quite an open problem. Then for LLM specifically, this we already mentioned, right, that the architectures are very different and the sizes of these models are different, which makes it challenging. I also like the question of personalization, which is very related to what I was saying, that what is the objective? Is the objective the sum of the agents, or is the objective individual, that every agent has their own objective, and then how do you achieve this in LLMs, where you try to take a big public model and personalize it to individual agents? I think we're only at the beginning of this. I think it's fascinating how this could be more decentralized again, right? Now the centralized model of LLMs could, hopefully some of these building blocks can in the future enable like more privacy-preserving training and also usage in general of these large foundation models. And that's it for now. Looking forward to some questions.
So yes, if anyone has questions, please feel free to ask them.
Hi, Martin. Thank you for the talk and about this prediction consensus. Can you say a few words more?
Yes. So that's this one here. You're trying to. So the nice thing is we don't assume anything about these agents or the data. So it can be arbitrary. Like if you meet this auto agent on the street, you have no idea what is their data quality and so on. But then we ask them to make predictions on a holdout set. And that holdout set is crafted such that it's representative of everyone, not only that particular client. So, and then based on their predictions on this holdout set, we give them scores. And also, we are not really sure ourselves, right? Because we don't have the labels on this holdout set. But that's where this last aspect, the consensus aspect, comes in. So we also see what other people think about that holdout set. And based, if then this potential collaborator agrees or disagrees with the consensus, then that's how we judge them. So, because also when you have very little data, it's hard, right? You easily become overconfident on your own data. You should not, because you have too little data to even know. So then we want to have consensus of everyone on what is the score of everyone. And everyone has a bit of a domain shift, right? Everyone has slightly different data set, which they contribute to the holdout set as well. The consensus is actually during the training, so this is always incremental. So you improve the consensus, and then everyone improves the model, and then you do the consensus again. So it's nice to interleave the two.
Okay, I think there is another question there, and then one from here.
Yeah, thank you very much. I would have a question to how do you think it's possible to stay robust and keep learning even when there are more than 50% of malicious clients? Is that possible?
I love this question. Yeah, can you tolerate more than 50% malicious ones? And in distributed computing, this is a very well-studied area to achieve exact consensus, and their answer is no. But in machine learning, I actually think the answer might be yes, and it depends what's the objective again. So that's always the crucial thing. And one thing we think we can do is if we do personalized learning, when you can say everyone trusts their own data even a bit more, right? I want to do a mix of my own task where I have my own data, and I always trust my own data, right? And in addition, I get a little bit of help from the others. So what that does is that now suddenly you trust 80% of the whole world, right? Because you gave 80% away to yourself. And then I think we can also tolerate more than 50% malicious ones, yeah. But this we haven't completely formalized yet, but I think there's some settings where you could tolerate more, and yeah.
Thank you.
Maybe I can ask a question. It's on your right. I'm on your right. Hey, Martin. So because we're at Hessian.ai, I thought I'll ask this question. So do you think computation or estimation of Hessian, is it absolutely necessary, somewhat necessary, or not required?
I like this question. I don't know the answer. So for one thing would be for collaborative selection, and the other thing would be for optimization. So can I speed up my optimization? And there I think the jury is still out if you can really benefit from Hessian information or not. So we see a lot, the most successful methods in transformers and so on are using some kind of diagonal Hessian information at most. There's some debate on that. I'm very curious if something of the off diagonals could also help to have some cheaper preconditionals. But of course we cannot afford a full Hessian. So now everybody's using diagonals. So I think there is room, yeah. So it's a very interesting topic.
Okay, thank you. Any more questions? Okay, I think that's the last one then.
So when you were showing the updates, it looked like there was some sort of, you're doing some sort of like linear application of each of the contributions to each of the actors. And when you think of data privacy and you think of someone that, at least in Germany, in Europe, you're allowed to retrieve. So for instance, if I was to enter my data into the system, because of the GDPR, I'm allowed to then say subtract my data out of the system. Does this federated learning concept allow for the removal of either bad actors or people who then want to retrieve their data again from the system? Or is it so interdependent or like non-linear in the way that you're updating the system so that you have to basically retrain to to extract that again?
Yeah, I don't know the answer. What you're asking is if it can be, so this is called like unlearning, right? To do the complete unlearning again. This year is a nice challenge organized by Google actually at NeurIPS, which is exactly about this. Can you do unlearning? And I think this question is open even in the centralized case, and in the federated is also open. Yeah, it's a great question for LLMs. If there was like one data point where it was proprietary data, can you remove it from the weights? It's a very tricky question. I'd love to answer it, but I have no idea.
Okay, in this case, thank you again, and I have something for you. So, thank you.
So much.
Thank you again for this great talk.
Thank you.